So, जी
हमारी वेबसाइट बहाल हो गई है, यू कैन गो एंड विजिट इट।
आप लोग सब देख सकते हैं इसको, या इसको थोड़ा सा हटा दें ना? ठीक है, सबको नजर आ रहा है
और वीडियोस भी उस पर।
So this lecture is about, this is lecture 4. It's about linear vector fields. Matrix groups and exponential of matrices. So before taking up these things, there were two very important things which I forgot to do in the last, not forgot, there was no time to do them. Okay, so this is a carryover from the, so in the first lecture, in the last, if you look at the, from 57 minutes onwards, there's a half an hour discussion of groups, right? And the second lecture, I taught you how to find out tangent spaces to every subset of Rn. It doesn't have to be a sphere or ellipsoid, it can be intersection of a sphere with a plane or whatever, anything. You can, I taught you how to, working from equations, you can find out the tangent space. And why did we do that? Because we wanted to define what is a vector field, right? So what is a vector field? In my, how did I define it? What is a vector field to the plane? Come on, guys. Huh? Okay, if you can't, so how would I draw a tangent vector here? Yeah, show to me. What can you draw a tangent here at this point? Huh? Initial point will be point P, right? And this is your vector. Its component, how many, because we are in two dimension, how many components it will have? Two components, right? This will be AP and BP. A and B are functions of, and then to every such vector field we associated a differential operator of order, linear differential operator of order 1. So and what was that? For every function we take the directional derivative in the direction of the vector, and once we have done that, we can identify this vector field with the, so if the vector field V has components A and B, this gives rise to the differential operator dV, which is A times partial by partial x, B times partial by partial y, right? And this correspondence is unique. Every such operator comes from, of course, you can calculate what are A and B by just evaluating it at the functions x and y. And this is not only nothing special about 2, it works for any dimension whatsoever, okay? And why did we do this? Not we. This is due to sophistry, that you can put an extra structure by taking the Lie derivative, by taking the commutator of these operators, okay? Then it becomes a Lie algebra. And there is one identity which I have to verify today for you, Jacobi identity, but before that, something very important from last lecture. So V is a vector field defined on an open set U of Rn. Okay. Let's see from an interval I. I don't want to use A, B. Just let's give it some. From I is equal to xi, from an interval I to Rn be an integral curve. OV. So here, of course, here I is an interval, I is an open interval. Okay. So, of course, I can only draw pictures in on the board. So this is your curve. This is your point T. This is your curve C. So where is C prime T? This is the point. This is the point C of T, not T. This is the point C of T. So C prime T is tangent here, right? And to say that it is an integral curve, C is an integral by definition. C is an integral curve. Of V. This is the same as saying that C prime T. On the other hand, we have the vector field here, so we can talk about the value of the vector field at the point Ct. So C prime T is equal to V of Ct for all T in I. Okay. A theorem trivial to prove but extremely useful theorem. If f is a function defined on U and x of f is 0, then the function f of Ct the function f composed with C followed by f is constant. Oh, did I take for capital F or small f? Oh, okay. So what is? वो कपड़ा किधर चला गया? वो बोर्ड को साफ कर. नहीं कपड़ा भी था उससे. कपड़ा है? जी फिलहाल इससे कर ले. Okay. So, sorry I erased that. So we want to show, huh?
It worked too well.
Yes, I was too quick. But so once again, V is a vector field. On U and C is an integral curve. F is a function so that V of f is equal to 0, then f C composed with f is constant. So proof. How do you show that a function is constant? You just take the derivative. So we have to take we have to compute, we have to d by dt of f of ct. Okay. So now just to save time, I will assume that n is 2. Okay. So to save time, I assume that n is 2. Okay. So C is a function from an interval I into the plane, and C of t, what names do you want to give it to its components? XTYT or FTGT? What do you feel comfortable with? XTYT? Okay. 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 F is a function of from U into R. So remember, U is in something in 2 dimensions. So F is a function of 2 variables, x and y. So F composed with CT would be, therefore, so this is just undergraduate calculus. So therefore, ये क्यों बैक क्यों कर रहा है ये?
आप स्पीकर के नजदीक.
अच्छा, oh, ठीक है. So I should stay up to here, huh? Okay. So now F composed with CT is equal to F of xt and yt. Let's call it gt. So what is the chain rule now? What is g prime t? Partial f by partial x evaluated at the point xt and yt multiplied by x prime t plus partial f by partial y at xt yt by y prime t. So by chain rule, g prime t is equal to partial f by partial x evaluated at xt yt times x prime t multiplied by x prime t plus partial f by partial y at xt yt times y prime t. Okay. This is the same as what's partial f by partial x, partial f by partial y? That's the gradient of the function, right? So this is gradient of f gradient of f at xt yt dot x prime t and y prime t, which was c prime t. Right? And what was our what was the definition of what was v of f? If v is v of f, this function at any point p was gradient of f dot the vector value of the vector field v at p. This is how we associate it to any vector a differential operator. So what does this equation tell you? Therefore, g prime t is equal to the vector field. One more. C prime t was, because the integral curve, this is equal to gradient of f at x t by t dot the value of the vector field v at the point c, not c prime t, c t. Otherwise, we will not be able. Therefore, g prime t is equal to vf evaluated at the point ct. Xt yt was ct, right? So, but what did we assume? Vf was always 0. So, this is 0. Therefore, g is a constant. Okay. So that is the importance of the when you find out infinitesimal criterion, xf is equal to 0 is easy to compute, and then you can conclude that this function is constant on all the integral curves. Okay. So can I erase this now? Okay. किसे? वो आप करिए अपने फ्री टाइम में. अगर मैं इसमें रिलेट करने लगा, सबसे पहले तो मुझे इलेक्ट्रोमैग्नेटिज्म आता ही नहीं है, ठीक है. और दूसरी बात, अगर मैं करने लगूँ तो आई विल नॉट बी एबल टू फिनिश व्हाट आई वांट टू. Okay. So example. We look at this constant vector field. V at any point P is the vector. Let's stay in 2D, right? So what is it as a differential operator? देखिए एक सेकेंड, अगर आपके पास वेक्टर फील्ड V है, उसके कंपोनेंट्स A and B हैं, these are functions of point P. So as a differential operator, what is it? Which I identify is A partial by partial x plus B partial by partial y. So what is the corresponding differential operator? Partial by partial x. So right. And now what are the what does xv equal to 0? V of f is equal to 0 if and only if partial f by partial x is equal to 0, right? So this means that f should be just a function of y. So f of xy is equal to g of y, right? Okay. What were the integral curves of this? So we computed last time the integral curves of v through the point xy is c of t x plus t comma y. Okay. So is f constant on any integral curve? By the theorem it must be, because f is just a function of y. So therefore f of ct is equal to g of, so it is constant on, so on every integral curve. So how does it look like pictorially? What are the integral? This is the origin. So the integral curves are, and because the function f depends only on the y coordinates, this is an example. You know, it may look to you like a trivial example, but I'll show to you a fantastic result later, that if I give you any vector field, you can introduce coordinates so that away from its zeros, where it is identically 0, you can introduce coordinates so that the vector field is partial by partial x. Okay? And if I give you two vector fields whose Lie bracket is 0 and they are linearly independent at a point, then you can introduce local coordinates. So let's call these local coordinates x and y, so that v is partial by partial x, and the other one v and w commute, w is partial by partial y. Similarly, if I have k vector fields which mutually commute and they are linearly independent at a given point, then you can introduce local coordinates x1 up to xn. So the first field is partial by partial x1, second field is partial by partial x2, and so on. Okay, this is an extremely useful result. I will tell you how to do it algorithmically. Yes.
So can we say that for such fields we can also introduce?
G.
So can we say that for such a fields we can always introduce coordinates that in which these fields are one dimensional?
No, for commuting fields.
For commuting fields.
For commuting fields, you can introduce coordinates so that, and if you have commuting field and they are linearly independent at a point, you can introduce coordinates so that the first field becomes partial by partial x1 and the second one partial by partial x2. Yeah.
X2.
Yeah.
Okay.
But it's very important, they should be linearly independent.
Okay.
Okay?
Okay.
I give you a counter example right now. So let's say V1 is partial by partial x and V2 is x times partial by partial x. Okay? Are they dependent or linearly independent at any point? Okay, let's check. So take a point P. Okay, so P will have some coordinates. What do you want to call the coordinates? Huh? Okay, let's call let's not call, let's call it xi, a and b were reserved for functions, right? Okay. So what is v1? Is partial by partial x at the point, is just, and v2 at the point, and v2 was xi times partial by partial x at the point xi eta. Are they dependent or independent? This is, I'm not varying xi, I'm saying at the point, this one is a multiple of this one. So at the point P, they are linearly dependent, right? And so this is true for any point, right? So we don't want to get into this. I'll do it. As vector fields, they are linearly independent, but the values at every point are dependent, right? Because as vector field, if you yeah, okay, I don't want to waste more time, but it's a subtle point. It's confusing, but so. By the way, the notes for these will be available eventually on the website, and after I am finished, I will put them up also on archive as what should we call them, lectures or black hole lectures on something like this. We'll give some title so that people can refer to them, and those lectures will be a little bit more expanded. Okay, so even if we can't cover the whole thing, it's better for you to understand something than to just rush through the syllabus. Okay. Okay. So now the other thing was the Jacobi identity. So last time I forgot to give you a proof of the Jacobi identity. So Jacobi identity. So let x, y, and z be vector fields. Vector fields on an open set of By the way, why do I always take an open set U in Rn? Because what Parvez is doing is not different from that. Because every manifold is locally a piece of Rn, right? And you define these vector field and all these invariantly. So when you want to calculate, you have to use coordinates, local coordinates. These coordinates may not be defined everywhere, but in a neighborhood of a point, they are one-to-one functions. Okay, and then you once you have defined something geometrically, then you can take any representation you like and you work with that. Okay, so so the Jacobi identity is this. Let J of x, y, z be equal to bracket of x, y, z plus bracket of y with z is zx plus bracket of z with x and y. Okay. So I saw a beautiful proof. It was given an exercise, and once I looked at this exercise, then I solved it myself, and that's why I never forgot it. I did not go and consult any literature. Okay. And I think this proof is either due to Chevrolet or Jacobson, I don't know. Because I asked AI and it said I can't confirm, but that's probably the most likely answer. Okay? So, proof. First, prove that if prove that if if A, B, C are linear transformations, of a vector space capital V because I've used V for so many times. Then, and we defined A bracket B to be AB minus BA. By the way, if I take two linear transformations, is their composition a linear transformation? Linear transformation का मतलब क्या है?
सर लीनियर ट्रांसफॉर्मेशन का मतलब ये है कि जब हमारे पास दो वेक्टर्स सम में लिखे हुए हैं तो हम पहले सम लेके उनकी ट्रांसफॉर्मेशन ले या ट्रांसफॉर्मेशन ले के सम लें तो वो बराबर होंगे.
और एक और one small thing that if we call this linear transformation T, T of C times V, where V is a vector, is C times T of V.
Exactly, scalars.
Yes, scalar, बिल्कुल. And T of V1 plus V2 is equal to TV1 plus TV2. Now, when you compute, you will find out that the composition of two linear transformations is again a linear transformation.
Yes.
And therefore, this difference will be also a linear transformation. Okay. Then if we said if we said J of ABC is equal to, what did I take X on? A bracket plus B bracket C bracket A plus C bracket A bracket B. If a computation shows that J is 0, and this, because it's straightforward, I will not do it, you do it as a homework. Then a computation shows J of A, B, C is equal to 0. This is completely straightforward. You have to be careful that you don't make a sign mistake, and if you do it, you will see everything will cancel out. Okay. So we want to use this fact to now. So this was step 1, and step 2 is use 1 to prove G of X, Y, Z is equal to 0. Okay. So we have to.
I will have to say that this thing, the Jacobi identity or Jacobi identity is proved for this operation, this computation operation, right? Because
That's what I'm. Ji.
yeah, so for a certain operation, you prove that. So here,
No, I did not prove it yet. I forgot. This was. I should have done it last lecture. There was no time.
no, that's how when we say this is this. So under the operation of
Commutator.
commutation, it satisfies the
Jacobi.
Jacobi identity.
Ji, ji, ji. So I say you reduce it to a proof for linear transformations.
Yeah.
If you once you have done it, then so now I have to come up with a vector space. So let so these fields were defined on some open set U of Rn. Let V be the vector space of all differentiable functions on U. By differentiable functions, I mean they can be technically we say C infinity functions, means you can differentiate them as much as you like. Okay. So to every to the vector field X, we associate a linear transformation dx from capital V to capital V by dx of f is x operating on f. Is it a linear transformation? Because these are just some a times partial by partial x plus b times partial by partial y and so on applied to f plus g would be it's you can check it's linear over it's a linear transformation of this. This is an infinite dimensional space, but still it is a you can talk about why not you can talk about vector space of infinite dimension. It's staring it right in the face. All the set of all continuous functions is an infinite dimensional space. Okay, but that shouldn't bother us. So this is a linear transformation. And now, moreover, you can check that dx bracket dy is d of x bracket y. Okay, this just follows from the definitions. So therefore, j of dx dy is this is of j of x y z, right? Now because okay, this is a vector field, right? Composition of two vector fields was a vector field, right? So j of x y z is sigma. We don't care what sigma I is equal to 1 up to n ai partial by partial xi, and now we test it. If therefore so okay, And this one was, we just proved, what was it? dj, this was equal to 0, right? Because we verified the, not verified, I gave you the homework that for when you take linear transformations, their triple product is always 0. So therefore j of xy, therefore sigma ai d by dxi evaluated at xj is aj is equal to 0 for all j. Hence j of xyz is also 0. Okay. So this is a coordinate free proof of the Jacobi identity, conceptual proof. You reduce it to something where you can verify it easily. Okay. So this was what's the time now?
We still have more than 3/4 of an hour.
Wonderful. Okay. So this was what I wanted to do in the last lecture, but there was no time. So okay. Okay. So now I come to the point of linear vector fields. Okay. So let A be any n by n matrix. Okay. Then A defines a linear transformation L sub A from Rn to defined given by LA of x1 up to LLA x1 up to xn is equal to A times x1 up to xn. Okay. So if A is Aij, what are the components of this? What's the first component? Let's suppose that if A has components, ijth entry is Aij, then what is A of x1 would be LA of x1 xn. The first A11 x1 plus A12 x2 plus A1n xn and so on. A(n1) x1 plus A(n2) x2 plus A(n)n xn. Okay. And what will be the corresponding vector field? You just put partial by partial xn1 here, and for the next, so corresponding vector field is is a11 x1 plus a1 and xn partial by partial x1, and the last one will be plus a n1 x1 plus a n n xn partial by partial xn, and in sigma notation this will be sigma aij xi no xj, right, aij xj partial by partial xi I between 1 and okay. Exercise and no, first of notation. So
These are all transformations within
these are all linear transformations.
on the same tangent space.
No, they are linear transformation on Rn.
Yeah, but you are at a point.
No. This
I'm comparing vectors at
I'm saying
within the same tangent plane.
no. These are vector fields defined on for matrices. These are vector fields defined everywhere. Ignorant. No, this is very important. I will answer it with an example. Just let me state this and then I will. Okay. So exercise. Show that LA bracket LB I would have liked it to be L of A bracket B, but unfortunately the sign reverses. This is L of BA. Okay? But it's very close. Now, Pervez. So, let's take an example which we are going to see 1000 times. Example. Let I be this one. Right? So, what is the linear transformation defined by I? So Li of xy is equal to 0, 1 minus 1, 0 of xy. What is it? Yns and what is the vector field defined by this function? Huh? Y minus x partial by partial y. So the corresponding vector field is, let's give it some name, V of I. This is y partial by partial x minus x partial by partial y. Is it familiar to you? I think you have seen it. Pervez, did you already discuss it?
This is the generator of rotations.
Ah, of course. But you have discussed it with them already or not yet? Okay.
But the reason I asked that question is that, okay, you're in Rn. Rn is flat.
Rn is flat.
And what we do is we take the partial derivatives as being the unit vectors, but those are different at different points on a curved manner.
Here also they are different on different points. They keep on varying from.
Then I asked, is this on the tangent plane or not? And you said no.
No, its value at every point is a tangent vector, but the whole thing is changes from points to points, just as you do.
So d by dx1 means what?
Yeah.
Partial by partial x1.
Yeah. So d by dx1 as a geometric vector field, it means you. So let's say we are in two dimensions, right? Here is this point. It means this is the point x1, x2. D by d. So as a geometric operator, it corresponds to the unit vector in parallel to the x-axis, and the corresponding differential operator is differentiated directional derivative in this direction.
Yeah. Except that this is on a flat space. If you were on a manifold, then d by dx1 would mean different, something different here as compared to here.
No, you cannot talk about d by dx1 on a manifold unless you choose local coordinates.
Yeah, we are.
So once you choose local coordinate, you are back in flat space.
So this is a tangent plane.
It's if you want to use technical language, it's a tangent bundle. Tangent plane is a vector space only at one point.
At one point.
And when you look at all the tangent spaces, you get the union of that's called the tangent bundle. For example, see, on flat it's difficult to see, but on curved, for example, look at the circle, right? So you have at every point you have a tangent. Okay, and you can so this vector is perpendicular to this is the origin. So this is perpendicular to this. If you take the cross product, you will get a cylinder. Okay. So then you can straighten it out, and it will become a okay. So the tangent bundle of the circle would be, in this case we can picturize it. It will be a cylinder. Okay. And the tangent bundle of the sphere would be S2 cross S2 cross R2. Okay. Is it clear now? Okay. So from now on, to save time, I'll try to state things in as general as possible, but for example, I will just do n is equal to 2. So now I will assume that, to save time, I will take n is equal to 2. Okay. So let A be, let's give it some name. Doesn't matter. Let A be equal to, what do you want to call it? Alpha, beta, gamma, delta. These are scalars. Okay. And And what is the linear transformation? LA of xy is equal to alpha, beta, gamma, delta xy. Okay. So an integral curve of, okay, and dA, the corresponding differential operator. So what is dA? Yes. What is alpha x plus beta y, gamma x plus delta y, right, as functions, and then this will translate to the operation of taking directional derivative in the direction of the field. So this is alpha x plus beta y d by dx plus gamma x plus delta y d by dy. Okay. So an integral curve of the field given by A is a curve, integral curve of the field passing through the point xy through xy at time t equal to 0 is a curve C from minus epsilon to epsilon into R2, C of t is equal to xt by t, and C of 0 equal to, it's unfortunate notation, but maybe we should have called it, but you said you call it xt. In my notes I'd called them ft and gt, but I should not have agreed to you, but now we have, but it's understood, right? This x is different from this x. Okay, so it's a curve CT such that x prime t, y prime t is equal to a times xt by t. And of course C of 0 is the point xy. Now does it not look very familiar? So if you write it like this, d by dt, this is the definition of the integral curve. But I'm trying to relate it with what Dr. Vakas did today with you. Right? So if we could somehow define the exponential of a matrix, then we would get our integral curves. So, okay. So looks like asking for definition of exponentials. Okay, and indeed there is a definition. So what was the definition of e to the power of something, or e to the power of x? What was the Maclaurin series? 1 plus x square and so on, right? Okay. A matrix, where does it live? The 2 by 2 matrix, how many entries do you need? 4. So it's an element of a 4 dimensional, right? So I could, if we can define distance between points in a, what's the distance between point, let's say in 4, what's the distance between points A, B and C, D in 2 dimensions? What is it? A minus A1 whole square plus B minus B1 whole square and then square root. What's the distance between point A, B, C, the first point, and the second is D, E, F? Is A minus D whole square plus B, I even forgotten. The first point is A, B and C. And the second point is D, E and F. So what's the distance between P and Q? A minus D whole square plus B minus E whole square plus C minus F whole square and then the square root. And the same you can do for distance between 2 matrices, right? And then you can talk about series of matrices when they are convergent, when each of the, so if I take a matrix value, if I take a matrix with functions as entries, when will it converge? When every entry converges, right? When the whole of the analysis you can repeat for matrices. You can talk about convergent power series, about Cauchy sequences and everything, okay? So here's now the formal definition. So let A be n by n matrix. Oh. This means it's a matrix with constant entries, okay? We define e to the A as the identity plus A square 2 factorial, so this is sigma A to the power of n over n factorial and from 0 to infinity, okay? And you can check that this series will converge, okay? In the notes, I'll give you some references where you can read all these things, right? These are points of analysis. If you do that, we will not get anywhere, okay? So and therefore we define, therefore e to the TA e to the TA is 1 plus TA plus TA square and so on, plus Tn an over n factorial and other terms. And this series is convergent for every T. Okay. Okay. So let me give you an example. G. Oh, one identity TA plus T square A square over 2 factorial plus T and an over n factorial and so on. So in sigma notation is sigma T to the n A to the n over n factorial and from 0 to infinity. Okay? Okay. So now okay, examples. Let A be equal to 0, 1 and 0, 0. What is e to the power of TA? there's no way for me but to work it out. Okay, so e to the Ta is identity 1 0 0 1 plus t times 0 1 0 0 plus t square over and so on. Now what is t square? Sorry, what is a square? Okay, so what is a square? 0 1 0 0 times 0 1 0 0. If you multiply this out, this will just be the zero matrix. So everything will collapse, and thus therefore e to the power of Ta is 1 0 0 1 plus t times 0 1 0 0, and when you add it, what do you get? 1 and then t and 0 and 1. So exponential of t is something very simple. Okay. Okay, and example, let A be equal to lambda mu. So diagonal matrix. Here lambda mu are constants. So what do you guess? What is e to the power of what is e to the power of A? Yeah, e to the power of A would be, if you take lambda 0 times 0 mu multiplied by lambda 0 times 0 mu, you get lambda square and mu square. So what is your guess? It would be e to, no, 1 plus lambda square over 2 factorial and so on. So this will be e to the power of lambda. This will be e to the power of lambda 0 0 e to the power of mu. And so e to the power of Ta would be e to the power of t lambda 0 0 e to the power of t mu. Okay. And the next two examples I'm going to leave for you as homework. So A is equal to 0 1 0 1 1 0, right? Then e to the power of Ta is cos t sinh t okay, and so you just write down the definition, compute the square of this, and you will get it. You just have to do some work. Okay, it's a very good exercise, and so homework. And then you take A equal to 0 1 minus 1 0, then e to the power of Ta is cos t sin t minus sin t cos t. Okay. Okay. And notice that always e to the power of t plus SA is equal to e to the power of TA multiplied by e to the power of SA. Okay. So okay. So definitely one parameter subgroups of GL and R. Okay. So this is by definition a one parameter subgroup is a function phi from R to GL and R with phi of 0 equal to the identity and phi of S plus T is equal to phi S multiplied by phi T. Okay. So it's a homomorphism from the additive group to GL and R. And I'm now going to show to you that all one parameter subgroups are exponential of a matrix. Okay. So that's why this comes up. So
Hassan sir, what is N here?
any integer, this capital N. GL and R means all n by n matrices whose determinant is not 0. Right? SL and R will be all those whose determinant is 1. Okay. So theorem. All one parameter subgroups.
Just a question. So
Ji.
when you, let's say, do a Wronskian and you say determinant should not be equal to 0 and you establish linear dependence or independence, whatever.
Ji. But that's over functions.
Over
Huh?
functions, yeah.
Ji.
Over here, when you say whether the determinant is 0 or non-zero, so essentially, what is it that we are establishing by saying that?
That it is an invertible transformation. It has an inverse. Right?
Okay, right.
That's
Because if the determinant is 0, then A inverse doesn't exist.
A inverse doesn't exist. जी जी बिल्कुल फिर ग्रुप नहीं बनता yeah okay all one parameter subgroups of GL and R are of the form T goes to e to the power of TA for a suitable matrix A. Okay. Okay. So just to save time, I will do it for proof for n is equal to 2. Same for any n. Okay. So let phi from R to GRNR be a one parameter subgroup. Okay, so phi t plus S is equal to phi t composed with phi S. And of course, the only tool we can use is calculus, right? So let us compute phi prime t. Phi prime t is as in FSC. What is f prime t? Limit of f t plus h minus f t divided by h as h goes to 0. And since phi t is a point in some Euclidean space, we can repeat the same thing. So, now phi prime t is limit of phi t plus h minus phi t divided by h as h goes to 0. Okay, this is the same as limit as h goes to 0. Now I use the fact that it is a homomorphism. This will be phi t composed with phi h minus phi t divided by h, right? And this is this I can factor out phi t. This is phi h minus what is when I factor it out, what will be left here? Identity, right? And what is identity? Phi of 0. This is phi t phi h so because t behaves like a constant here, you can bring the interchange phi t and the limit, and you will get phi t times phi prime 0, right? So this is equal to phi t times phi prime 0, and this is the same as phi prime 0 times also multiplied by phi t. Okay. Now what is this? Phi prime 0 is some matrix. Let A be equal to okay. So phi t. So phi prime t is equal to A times phi t. Okay. Okay. On the other hand, if fct is equal to e to the power of ta is a one parameter subgroup with fc prime t is equal to a times fct, a times e to the power of ta is equal to a times fct, and fc of 0 is the identity. Now when you think of this will be a system of ODEs, and by the existence and uniqueness theorem it will have only one solution, right? So phi t must be equal to epsilon t. So by the uniqueness theorem for existence of for systems of ODEs, you get phi t, because these are two functions whose value at one point is the same and the derivatives are the same. Okay, but there is a completely straightforward proof which I have given you as a homework. Let me outline. So alternative proof. So homework. If phi is a one parameter subgroup and phi prime 0 is A and epsilon t e to the ta, show that d by dt of phi t epsilon t inverse. Here you are going to use the product rule, but keep in mind that these don't commute, so you have to be a little bit careful. But if you do it, you will see, you will learn a lot, and you will see that this is constant, and its value at identity is phi 0 time epsilon 0 is 1. So because it is constant, phi t times epsilon t inverse must be equal to the identity. So phi t is equal to epsilon t. So all parameter subgroups are like this. Okay. I still have half an hour, right?
5 minutes.
5 minutes. Okay, we'll carry over next time. So now this is orthogonal groups. Okay. See, if I give you two vectors, this is V1 and this is V2, and the angle between them is theta. If I rotate all this through any angle, so suppose and then this angle is also theta. So the transformations which preserve lengths and angles are called orthogonal transformations. Actually, angles will automatically be preserved, but so how do you define What's the dot product of V1 and V2? So let's say V1 has components AB, A1, B1, and V2 has components A2, B2. What is the dot product of V1 and V2? Is A1 plus B1, B2, right? Do you know that if I take two numbers, x and y, x times y, is it linear in x? If x1 plus x2 times y is equal to x1y plus x2y, and x times y1 plus y2 is xy1 plus xy2, right? It's linear in both, and something linear in both, it's multilinear, and multilinear functions are called tensors. So there is no difference between. So the best example of a tensor is your good old multiplication which you learnt in kindergarten. But of course your teacher didn't say it's a tensor. So okay, so how can we generalize it? So an orthogonal transformation is a transformation which preserves this. So G is orthogonal. G is orthogonal if GV1 dot GV2 is equal to V1 dot V2. Okay? Okay? So to generalize this, we have to look at, we have to generalize this inner product. Okay? So generalization. Let B be any n by n matrix. Okay. Let x be a vector in Rn with component x1 next to xn, and y be. Okay. So we define a function from. This is a generalization of the inner product. Right? We define a function from Rn cross Rn into reals by B of. We define a function denoted by these angle brackets, and we put here V, where x. Remember, x was a. So we take x transpose B and y. So what is it? Is it a scalar or a? It's a scalar, right? This is 1 by n times n by n is 1 by n times n by 1 will be 1 by 1 matrix, and that is a scalar. Okay. So a transformation T, by definition, a transformation, a linear, a non-singular, it will automatically be okay. Okay, a transformation T G is called orthogonal for the inner product for the bilinear function. If gx gy is equal to x bracket for all xy. Okay, and it's very clumsy to, so by abuse of notation we write as B of xy. Okay, so B for bilinear and B also for that matrix. Okay, and you get your good old inner product by taking B equal to what? 1 1 1 1, right? So SO2 for O2 you would take your matrix to be diagonal with entries 1 and 1. For O1 minus 1 you will take 1 minus 1. For OPQ we will take P pluses and Q minuses, and this OPQ is very O31 is your Lorentz special, it comes in a special relativity. Okay. Now there was nothing special about, you could take B to be a complex one, and then you can define how you define an inner product on C2. Z1 Z2 inner product W1 W2 is Z1 W1 conjugate plus Z2 W2 conjugate. So you can define a Hermitian inner product here by writing this. Where did it form? Where was my X transpose B Y conjugate, or maybe it is X conjugate here. Here. Okay. So then you can define your unitary groups and so on exactly in the same way. There is nothing mysterious about SU2. Okay, something mathematically it's something very simple. Okay, so we will continue with this next time, but I will need 5 more minutes to finish it next time. But yeah, okay.